Hello everyone. Now if you look at the heading, I have written here second law of thermodynamics. And second law of thermodynamics, the statement is actually this, that total entropy of the system and its surrounding increases in a spontaneous reaction. Now what is the meaning of spontaneous reaction? A reaction which moves in a particular direction, okay, without any external influence. Now in order to understand this statement, this second law of thermodynamics, that entropy of the system, okay, that is entropy of the system plus entropy of surrounding increases in a spontaneous process. Let us understand what is the meaning of entropy first of all. Okay, now just look at this these pictures, whatever I have drawn here. We are having ice, we are having water in the form of liquid, and we are having water in the form of gas. Now what do we see? In case of ice, the molecules are existing in a proper ordered state, whereas the water molecules, when we convert this ice into water in the liquid state, you can see that the distance between the molecules got increased, isn't it? Now there is disorder in the particular state, okay, because molecules are moving randomly here and there. But when same water is heated further, okay, we'll be getting gas. Now in case of gaseous molecules, the degree of randomness is more. The degree of randomness is more, and this degree of randomness, this extent of randomness is called as entropy. Okay, so entropy means it is a measure of, entropy is defined as a measure of disorder or randomness in a system. So second law of thermodynamics states that for a reaction to be spontaneous, the condition is that total entropy of the system, okay, total entropy of the system as well as surrounding, okay, system as well as surrounding, that is total entropy, okay, it has to increase. So we write that total entropy has to be more than 0, then and then only the reaction will be spontaneous. It means then only the reaction will take place. Now as you can see, there is one reaction wherein iodine solid, okay, when aqueous medium is added to iodine solid, it becomes iodine aqueous. So it means earlier it was in solid state and now it has moved into the liquid state. So what happens in this case? The measure of disorder has increased. So we say that in this particular example, change in entropy has increased, that is change in entropy has increased, so it is positive. In this second case, if you see, hydrogen molecule, see, one hydrogen molecule got converted to 2 atoms of hydrogen. Now even though here also gaseous state is there, in the product also gaseous state is there, still we would say that entropy has increased because earlier it was 1, now it is 2. Okay, so quantity wise if you see, the randomness has increased. Okay, but students, how to measure the entropy? Because entropy is a measure of disorder. How will you measure that entropy has increased or decreased? So it is not possible to measure entropy exactly, but yes, one can measure change in entropy. Okay, one can measure change in entropy. Now how we can measure change in entropy? Suppose we are having a beaker, okay, and we are having some liquid into it, fine, and the initial temperature is, let us say the initial temperature now it is 298, it is the room temperature. Okay, so we are having a beaker and beaker is having some liquid into it, fine. Now we are providing some amount of heat to it. So when you provide heat to this particular beaker containing liquid, what will happen? Its entropy is going to increase. But How will you measure that how much entropy has increased? You will measure if you are able to measure that how much heat you have provided and what temperature you have provided that heat. Okay, so with this I come to the formula of change in entropy, that is delta S is equal to Q reversible upon T. Now students, T over here is the temperature at which you are providing heat to that particular system. Okay, so in this example our T, it is 298. Okay, and suppose you are providing heat to a particular container or to a particular system, and this heat happens to be 572 kilojoules. Okay, you are providing this much amount of heat, isn't it? So I will write here 572, okay, into 1000. If I write, it is joules. So for this particular example we will solve delta S is equal to Q reversible. Now students, why it is written Q reversible? See, in this example case 1 I have added the heat into it, isn't it? Now we can remove heat, we can remove this heat. Now when you remove the heat out, okay, and you can add the heat, it means this Q is reversible. Okay, you can provide heat to the system, you can remove heat from the system, but you should know at what temperature are you giving heat or you are releasing heat from a particular system. Okay, so if this is a particular system, okay, and if this is a particular system, if you are providing heat to this particular system, what will happen? Its entropy change will increase. Okay, but if the heat is released out, if the heat is released out, in this case what is going to happen is entropy is going to decrease. Okay, so if heat is absorbed by the system, if heat is absorbed by the system, it means system has acquired that much heat, but surrounding has lost. Okay, surrounding has lost. Fine. In second case, if the heat is released from the system, it means surrounding, in the surrounding that heat has been added. Okay, remember this, that when heat is absorbed by the system, in this case when heat is absorbed by the system, okay, delta S of the surrounding would be negative and delta S of the system would be positive. Okay, and in this case when the heat is given out, okay, when the heat is given out, it means that surroundings heat, okay, in the surrounding heat has been added, but the system has lost its heat. So in this way we have to remember. Okay, now so let us have better understanding of change in entropy. Suppose you have been given this reaction, that hydrogen gas reacting with oxygen gas forming water molecule in the form of liquid, and in this case they have given delta S is minus 327, okay, minus 327 joule per Kelvin, and they have given delta H is equal to minus 572 kilojoules. Okay, and the question is find out S total. Okay, now how we are going to find out this S total? Fine, S total we can find out if we know that what is Q reversible upon temperature. Okay, at what temperature was the heat provided to the system. Okay, now for this case we are having standard temperature pressure. Fine, so temperature would be 298 Kelvin. But what is this Q reversible? Let us understand the relation between Q reversible and delta H. So we know that delta H is equal to delta U plus P delta V. Okay, from the first law of thermodynamics we know that delta U is equal to Q plus W. Fine. Now delta U is equal to Q at constant pressure. Okay, it will be P minus P external delta V. So hence we can write that Q is equal to delta U. See, I shift this towards the other side. So I'll get plus P delta V. Okay, so if you compare these two expressions, they are same. Hence we write that delta H is equal to Q reversible. Okay, but over here we have to remember one point, that if Q is positive, okay, so I write here delta S total is equal to Q reversible upon 298. See students, what you have to remember, I will just make a note of it in this column. If Q reversible, okay, if it is positive, it means that system has absorbed the heat. System has absorbed the heat. So the entropy of the system is going to be positive. But in this case, the entropy of surrounding would be negative, because from outside we are taking away the heat and we are introducing it into the system. Okay. Now in this example, if you see, it is written delta H is minus 572 kilojoules. What does it mean? It means that when the product is formed, 572 kilojoules of heat is given to the surrounding. Given to the surrounding means, in this case I would write it is minus delta H upon 298. Okay, so value of delta H is given minus 572. I'm converting it to joules, okay, upon 298. So when you solve this, okay, you would be getting answer as 1592. This is joules, this is Kelvin. So you will be getting joule per Kelvin. Now what we have to focus here is, it is positive. So we got delta S positive. It means this reaction is going to be spontaneous. Okay. Now in this section I would like to mention here, suppose the heat is removed from the system. From the system you are removing heat. It means Q is negative. Now Q is negative, it means from the system you have removed heat. It means the entropy of the system is negative. And since the heat has been removed out from the system, that heat got added into the surrounding. So in this case, entropy of the surrounding would be positive. Okay, so everything depends on Q reversible. Q reversible means the amount of heat which can be provided to the system, which can be removed from the system. So we got the answer of delta S total as 1592 joules per Kelvin. It means delta S total for that particular reaction was greater than 0. Okay. So if it is greater than 0, it means it is obeying second law of thermodynamics, which says that total entropy change of the system as well as surrounding has to be greater than 0. It should go on increasing. Okay. Now we write here, if it is 0, it means the reaction is spontaneous. Okay. Now if delta S total value is less than 0, it means the reaction is non-spontaneous. Okay. Whereas if you see the value of delta S total is 0, we say the reaction is at equilibrium. Okay. We will cover here now what is this Gibbs free energy. Okay. Now see, this Gibbs free energy is given by this mathematical expression, that is G is equal to H minus Ts, wherein G is the Gibbs free energy, H is the enthalpy, T is the temperature and S is the entropy. Okay. Now this H, T, S, they are all state functions. Okay. It is not possible to calculate G. Hence we calculate delta G. Delta G is equal to delta H minus temperature is constant, so we write delta S. Now we are going to see how using Gibbs free energy, okay, how using Gibbs free energy we can predict that reaction is going to be spontaneous. Okay, so we all know that delta S total, what does it mean? It means it is the entropy change of system plus entropy change of surrounding. Okay, just now we saw that the formula for entropy change of surrounding is minus delta H upon T, delta S total. Okay, delta S surrounding we have seen in our previous video, it is Q reversible upon T, okay, which can be written as minus delta H upon T. Please remember this, as you will not get this particular expression explained in your textbook and all. Okay, so now I am going to multiply this entire expression by T. Okay, so I will multiply this by T. Let us see what we get. So I write T delta S, it is actually subscript, is equal to T delta S. Students, delta S system can be written as only delta S also. So I write T delta H upon T. Now in this expression this will get cancelled, so we are getting finally T delta S total is equal to T delta S minus delta H. Okay, now you have to compare this expression, okay, with this particular expression. Okay, so we can write that T delta S total is equal to delta G, but sign is reversed, so we will write minus T over here. So we have to remember that delta G is equal to minus T delta S total. Now it will be easy for us to predict the spontaneity of the reaction. Now as I said, it will be easy now to predict the spontaneity of the reaction. How it is easy? Before we proceed, this much you should know that if delta S is greater than 0, if delta S is less than 0, if delta S is equal to 0. Okay, let us see now. Students, if delta S is greater than 0, if it is greater than 0, what does it mean? Delta S is positive. So if delta S is positive, okay, positive into negative, it means in this case our delta G would be negative. Okay, so this is the first case, and we know by this particular expression that when delta S is greater than 0, when delta S is positive, the reaction is spontaneous. Okay, now if delta S is negative, okay, delta S जो है वो negative है, तो negative into negative is what? Positive. So in this case delta S is negative, delta G would be greater than 0. And this we know it is non-spontaneous reaction. Okay, but when delta S is equal to 0, we have studied this, that reaction would be at equilibrium. Okay, so delta G also would be 0, क्योंकि जब आप delta S यहाँ पे 0 डाल दोगे तो पूरा आंसर 0 हो जाएगा. So in this way, so students, looking at the value of delta S and delta G, we can predict whether the reaction is spontaneous or not. Okay, now we will derive the relation between Gibbs function and equilibrium constant. Okay, now what is the relation? The Gibbs free energy change, the Gibbs free energy change for a reaction which is in equilibrium. So I put this sign over here, it is a reaction which is at equilibrium. Okay, that Gibbs free energy change is given by delta G is equal to delta G naught plus RT L N. Now if you remember, we write here K. Okay, why we are writing K? Because K means it is equilibrium constant. Okay, so I write here Kc, or I can write here Kp. But because the reaction is at equilibrium, isn't it? Reaction is at equilibrium, it means delta G value has to be 0. So therefore delta G naught for above reaction is minus RT ln K. Okay, now let us convert this log base E to log base 10. So multiply by 2.303 RT log of K. Okay, it can be Kc or it can be Kp. You can write here Kc or you can write here Kp. So basically the relation between delta G and delta G naught is given by this expression.